Okay, y'all. The urinary system, or the GU, which is genitourinary. Um, okay, so for the urinary system, you have the kidneys here. You have two located in the flank, more towards the back. You've got your ureters, which come down into the bladder. Then you've got the urethra, and then we pee it out. The act of actually peeing is known as micturition. You could actually say, I've got to go pee, or I've got to go micturate. Micturation station, which is the peeing station. But the act of micturation is the act of peeing. So kidneys, location of kidneys. Kidneys lie under the back muscles, behind parietal peritoneum, just above the waistline. Right kidney is usually a little lower than the left. You've got your renal cortex layer, which is the outer layer of the kidney, and you've got the renal medulla, which is the inner portion of the kidney. I'm sorry, so we're going to talk about the kidney first. Kidneys. Perfect. Kidneys, veins, ureters. Okay, you've got your renal cortex. This is all on the outside. Okay, then you've got your renal medulla, which is these upside down triangles, or these pyramid looking things. Okay, you've got your minor calyx, I believe. These are like funnels, small funnels. They're going to funnel fluid into your into your renal. No, I was right. From your minor calyx into your major calyx, and then your major calyx, which is this big one, will drain it into your renal pelvis and then into your ureter. Okay, same over here, the renal cortex, medulla, minor, major, pelvis, and then ureter. Well, let me go through that. You have a renal artery, and then you have a renal vein. This little slit right here, because you see it looks like a bean, this slit is actually known as your hilum, and this is where your artery and your vein enter, and nerves as well. Okay, your renal circulation. For the whole thing, you've got your renal artery, comes in, oxygenates, gives nutrients, all of that good stuff, and then comes out your renal vein. Let's go through these over here. So your renal pyramids are triangular divisions of the medulla. That's the triangles. Renal columns, cortical tissue that dips down between the renal pyramids. That's in between. Renal papilla, narrow innermost end of the pyramid, which is going to be the smaller part. Renal pelvis, expansion of upper end of the ureter, lies inside the kidney. Renal calyces, division of renal pelvis. Okay, interior of kidney composed of more than one microscopic nephron units. There are millions of nephrons. Okay, I need you to understand that of the kidney, it is the nephron that is the functional unit. Okay, so this is your nephron. Now we're about to talk about these parts, okay? So your renal corpuscle is going to be this whole thing, okay? This whole round circle, or this circle up here, okay? Let's see, this whole thing, okay? Including the glomerulus, including the Bowman's capsule. That is your renal corpuscle. So your Bowman capsule, these are the parts of the nephron. Your nephron sits inside your kidney. This thing up here, I don't want to show that picture. So these little lines that you see right here, these are all nephron units, okay? These are all nephrons. You have millions of them in here, okay? You have to have an open mind in nursing and really try and see this. If these are nephrons, you have, at the end of urine formation, you have a bunch of urine going into here from millions of nephrons. Okay, back to the nephron. So, so this is that renal pyramid. This is your nephron, okay? I'm trying to give you an idea, that's why. Okay, that's your nephron. And there's another nephron. Now, these do have two different ones. I don't want y'all to worry too much about that, okay? Okay, but these are your nephrons. You have your Bowman capsule. I'm trying to figure out a good place to start. So, when blood comes in, okay, because we got to take fluid. When we make urine, we take it from the blood, the fluid from the blood, okay? So it hits the renal artery. Remember from that hilum right here, it hits the renal artery. Remember all the veins and all the arteries go up. It hits a nephron. Then the blood comes into the nephron through afferent arteriole, AFFERENT arteriole. Afferent is arriving. So the blood is coming into the glomerulus. Once it is cleaned out, it will leave through the efferent arteriole, EFFERENT. Okay? Right here is your afferent, where it comes in, goes through all these little tubes, and then leaves your efferent. Okay, so you got your Bowman's capsule. Okay, let me say this. You got this glomerulus. This is like a ball of yarn. Okay, you can picture a ball of yarn covered by protective case. But these are capillaries, okay? Small capillaries that the blood goes through, okay? The blood goes through here, and because you see how wide the diameter is on these, the blood is flowing just fine through those. But once it hits those tiny, tiny arteries, once it hits the very tiny arteries, it builds pressure, because remember, resistance builds pressure. It was flowing just fine, but now that they got smaller, it needs to push harder, creating pressure. So when pressure hits in these small capillaries in the glomerulus, the extra fluid from the plasma, the proteins, the electrolytes, all sugar, everything is pushed out into this Bowman's capsule. Okay, when that stuff is pushed out, it's starting to create urine. It's not urine yet, but it's starting to create it. Okay, just like here. So you see how it's wide here, the artery, it hits the afferent arteriole, goes in here in the small capillaries. All the stuff is pushed out into the Bowman's capsule. Now, glomerulus, network of blood capillaries surrounded by your Bowman capsule. So just like I said, cortical nephrons are 85% total, located mostly in the renal cortex. Your juxtamedullary nephrons have an important role in concentrating urine, located near junction between cortex and medullary layers. All I need you to know is they're nephron units. They're the functional units of the kidneys. They do just about the same thing. One dips a little bit lower, which is where that salt and water and stuff, but just see them for now the same, okay? So those were the parts. I kind of went into what they did, but those are the parts. You got your Bowman's capsule, and you got your glomerulus, which sits inside your Bowman's capsule. Okay, and then inside there, this whole thing is your nephron. So your renal tubule. Proximal, you got these tubes, okay? These are your renal tubules. Convoluted, I believe in that video I sent you, he said they just mean windy and twisty. So don't let that confuse you, okay? Proximal means close. We remember that from week 1. Distal means further away. So you can see it gets further away from the glomerulus. So, as I said, once all that stuff is pushed out into the Bowman's capsule, the blood that's left leaves through the efferent arteriole, but then the stuff that's pushed out goes through those tubes right there. So it leaves the Bowman's capsule and they go through the proximal convoluted tube, at which point then they go to the loop of Henle, then they come to the distal convoluted tube, and then they come to the collecting duct. Okay, throughout that. So in here, everything is pushed out. Okay, everything from sugar, electrolytes, and everything is just pushed out. As that stuff moves through the tubes, whatever the body needs will reabsorb it into all these capillaries that are surrounding the tubes. They're close and they surround the tubes so that things can easily diffuse across when the body decides, you know what, we still need this sugar. You know what, we still need this protein. You know what, we still need this. Granted, I'm sorry, some things shouldn't be in our stuff. We still need this salt. We still need this water. We still need this stuff. So it absorbs directly back into the bloodstream. Okay, so that stuff moves through the proximal again, then down to the loop of Henle, then to the convoluted, then to the collecting duct. Proximal convoluted tube is the first segment. Henle loop extension of proximal tubule consists of descending limb, loop, and ascending limb. Distal convoluted extension of ascending limb of Henle loop. Collecting duct is your straight extension of your distal tubule. All right, so now that is our functional unit. We just went through everything, okay? Your collecting ducts, like I said, let's see if I can find a picture. Oh, perfect. You see it goes through here again, through all these tubes, collecting duct. The collecting duct then goes into, well, I want to go through that with y'all. Give me a second. So the collecting duct, again, all these ducts then go into the calyx right here, into the major, into the renal pelvis, and then into the ureter, okay? Don't get the collecting duct mixed up with the ureter. The nephron are the itty-bitty things inside the kidneys, and there's millions and millions of collecting ducts pouring into this part, then into the ureter. Okay, our kidney function is to excrete toxins and nitrogenous waste, regulate levels of many chemicals in the blood, maintain water balance. They help regulate blood pressure and volume. They regulate red blood cell production by secreting erythropoietin. If you work in a hospital, you'll find yourself giving erythropoietin because we want someone to regulate their red blood cell production, or we want them to make more, so we'll give them erythropoietin, which will stimulate the making in the bones of the red blood cells. Okay, it's going to maintain water balance, right? Because around here, if you saw that video, he was saying salt moves out, water moves in. So depending on what we need, it helps regulate blood pressure because by getting rid of water or keeping water will raise and lower our blood pressure. At the same time, on top of our kidney, we have our adrenal cortex, which releases aldosterone, which assists our kidneys in holding on to water to bring up our blood pressure as well. Okay, filtration. This basically filtrates. That's what it's doing here. Filtration goes on continuously in the renal corpuscles. Glomerular blood pressure causes water and dissolved substances to filter out of the glomeruli into the Bowman capsule. Normal glomerular filtration rate is 125 a minute. And that's why when we look at the GFR of people's blood test, you're going to see GFR, which is glomerular filtration rate. We want to make sure that it's filtrating at a certain rate, that it can take the medications we're giving them, that it can take the soda he's drinking, that it can take the water he's not drinking, but that things are filtering at a consistent speed. Okay, if the number starts to go down, that means their kidneys aren't working very well. We don't want to give them anything too hard. That's going to be too hard on the kidneys. Make them work harder. Okay, so this is your filtration, right? Like I said, because of the pressure, it's pushed out. Everything is pushed out. As it travels, we're going to absorb water, absorb salt, and then absorb water. We're going to absorb sugar here. Down here, we're also going to absorb water and salt. Over here, we're going to let out potassium, take in potassium, let out water, take in water. We're going to do all of that throughout. Movement, so reabsorption. After we've pushed everything out, now our body has pushed everything out and then decides what do we need to take back. That's reabsorption. Movement of substances out of the renal tubules into blood, into peritubular capillaries, which is all these surrounding the tubes. All of those surrounding the capillaries. Water, nutrients, and ions are reabsorbed. Water is reabsorbed by osmosis. This is where we see osmosis, right? Because water moves from higher to lower concentration. If we have a little bit of water, we need more water, that water is going to move by osmosis back into our capillaries, or vice versa, out of the capillaries into the tissues or into the tubules. Sodium reabsorption occurs in the Henle loop using countercurrent flow. Woo. Countercurrent mechanisms keep the medulla hypertonic, right? And I think that's what the guy said in the video that I sent you. In the medulla area where the loop of Henle goes, it keeps it hypertonic, meaning it keeps it salty, so that the kidney can reabsorb extra water, because water follows salt. Amount of sodium reabsorbed depends on your diet. More sodium intake equals less sodium reabsorbed. More sodium excreted in the urine. Chloride ions passively move into the blood owing to negative charge. Reabsorption of ions, reabsorption of glucose. Glucose is reabsorbed from the proximal tubules back into the blood for use as energy. If there is too much glucose, as in diabetes mellitus, blood concentration can reach a level called your renal threshold. Filtrate contains more glucose than can be reabsorbed. Glucose is left behind in the urine, and then we pee it out, and that's a sign of diabetes. Secretion, movement of substances into the urine in the distal and collecting ducts from the blood into your peritubular capillaries. Hydrogen ions, potassium, urea, uric acid, creatinine, and certain drugs are secreted by active transport. And ammonia is secreted by diffusion. Then it diffuses into the tubes where it joins the urine in the collecting duct and then empties into the calyx, into the pelvis, into the ureter. All right, control of our urine. Antidiuretic hormone, again, secreted by posterior pituitary, promotes water reabsorption by collecting ducts. So by the time the urine hits the collecting ducts, the ADH is going to have the collecting ducts reabsorb that water because we need it. Reduces urine volume, a salt and water retaining hormone. Aldosterone, secreted by the adrenal gland, triggers the ROS process, promotes sodium and water reabsorption, and nephron reduces urine volume. When we have low blood pressure, our ADH kicks in because we want to hold on to more water. When we have low blood pressure, our aldosterone kicks in because, again, we want to hold on to more water to add more volume to bring our blood pressure up. And I forgot what that means. Atrial nitric hormone, I gotta look that up again, y'all. One of the peptide hormones secreted by the atrial cells in the heart promotes loss of sodium and water into the kidney tubules, increases urine volume. So that is when our pressure is high and we want to get rid of fluid and salt. Okay, if y'all remember this right here, if my blood pressure goes down, our body is going to release renin. This is our ROS. R is renin. Then this renin is going to convert angiotensinogen into angiotensin 1A. Renin converts angiotensinogen into plasma let me say that one more time. Renin is released. Renin then turns angiotensinogen into angiotensin 1. Your angiotensin converting enzyme converts angiotensin 1 into angiotensin 2. This is like Superman eating something extra to turn into Superman, okay? So he is angiotensin 1 and he eats something which is your ACE to make him stronger that turns him into angiotensin 2. Your angiotensin 2 promotes vasoconstriction of your does that say arteries? Arterioles, meaning is going to constrict, causing resistance, and resistance is going to cause pressure to go up. At the same time, your ADH has kicked in and your aldosterone has kicked in to help keep more fluid while your vessels try and constrict to cause resistance, to cause your pressure to come back up. So your ROS kicks in during low blood pressure. Abnormal amounts of urine, anuria. A is without, urea is urine, so absence of urine. Oliguria, scanty amounts of urine, meaning just a little bit here and there. Poly is many, urea is urine, unusually large amount of urine. Okay, so moving from the kidneys, once it goes through all of that, right, goes to the collecting ducts, down the calyx, down the pelvis, then it hits the ureters. Okay, let me make sure I didn't want to go through this with y'all. Make sure I told y'all right. Blood flows. So one more time on this, filtrate. Remember I said because it gets smaller, pressure causes things to move out. Typically we shouldn't be losing red blood cells. Blood flows in through afferent arteriole. Pressure builds inside the glomerulus. Water and small solutes filter into the Bowman's capsule. In turn, that fluid filters into your renal tubules. Glomerular filtration rate should be constant despite changes in blood pressure. If flow is too high, the body will lose excessive water and nutrients. If flow is too low, tubules may reabsorb toxins. The longer things sit, like in your belly or in your kidneys and your bladder, things start to get reabsorbed. That's just the natural thing the body does. All right, your renin, this is the same thing we just went through, right? Your renin, angiotensin, aldosterone system. Woo! Where's one at, y'all? Okay, so our blood pressure goes low, okay? Comes in here, blood pressure goes low. We stimulate the renin. The renin turns angiotensinogen into angiotensin 1. Angiotensin 1 hits the lungs where it picks up ACE, right? It picks up that converting enzyme ACE. It takes a bite of that and it turns into super angiotensin 2. At that point, we stimulate the adrenal gland, which releases that aldosterone. So remember, all this, not only angiotensin, will cause an effect on the vessels to constrict it, to cause resistance, to cause pressure to go up. But at the same time, that will stimulate the adrenal gland to make aldosterone, like I just said, to make sure it reabsorbs salt and reabsorbs water, to create higher fluid volume in our vessels, to also bring our blood pressure up. We just went through that. Make sure y'all know this, if y'all can read that. Composition of urine consists 95% of water, 5% dissolved substance. Okay, so again, remember, we have millions of those functions in there. They empty into the calyx, the renal pelvis, and then into the ureter. Okay, so the ureter is a structure near a long tubes. The function is to drain urine from the renal pelvis to the urinary bladder. A urinalysis is an examination of the physical, chemical, and microscopic characteristics of urine. It may help determine the presence and nature of a pathological condition. meaning if there's glucose in the urine, there shouldn't be, so that's a possibility of diabetes. Meaning if there's high white blood cell count, there might be infection, things like that. That's why we have people pee. We dip the stick. Like at the last place I used to have to grab a little thing and squeezer thing and dip it on the different colors of the UA of the urinalysis. I would do it on a paper, clean it, sanitize it afterwards. But I do it in a little box or something like that. Would put little drops of urine on each one, and then we have to compare it to the bottle and read it ourselves. And this was not too long ago. So, okay. So your ureters are just a pathway to your bladder. So now our bladder is an elastic muscular organ capable of great expansion, lined with mucous membrane arranged in rugae, like stomach mucosa. The storage of urine before voiding and then voiding. Here's our bladder. Here's our bladder. So we see again our ureters. Our ureters come in and they connect into these holes right here. And then it fills up our bladder. Our bladder shrinks when it's empty. It expands when it's full. Okay, you got a peritoneum, which is the lining of really the cavity. Okay, the inside of it would be the other word. Rugae is like those wrinkles in there. Ureteral openings. I need you to know your detrusor muscle. You need to know your detrusor muscle. That is the muscle that expands and that shrinks, okay? Again, muscles, the concept of muscles is that they contract and they relax. They stretch, they contract, they relax. Okay, you've got external urinary sphincter, which is right here, and then you've got which allows us to go pee. You've got your internal sphincter, which holds urine in the bladder. And you can see our bladder here for females, and our uterus sits here. So when we get pregnant and that baby grows, that's why he's pushing on our bladder. Here's this is for the men. All right, my urethra. Narrow tube from the urinary bladder to the exterior, to the outside, lined with mucous membrane, opening of urethra to the exterior called urinary meatus. The function of it is passage of urine from the bladder to the outside of the body, passage of male reproductive for males, passage of male reproductive fluid from the body. The urethra does both. Micturition. Passage of urine from the body, also called urination or voiding. It is the act of peeing. I think I said that in the beginning. The act of urinating, the act of voiding, the act of peeing. Micturition. Regulatory sphincters, internal, we just went through there. Your internal is involuntary, your external is voluntary. Your bladder wall permits storage of urine. Initiated by the stretch reflex. So once it stretches too far, it sends a signal to our brain. And the bladder wall contracts. Internal sphincter relaxes, your external sphincter relaxes, and urination occurs. Enuresis is involuntary urination in a young child who should already be potty trained. Urinary retention, urine produced but not voided. Urinary suppression, no urine is produced but the bladder is normal. Urine is voided involuntary. The urge is incontinence. Urinalysis, make sure y'all read this. We're looking at coca, right? The color, the amount, the odor, and the consistency. So turbidity, odor, specific gravity are used as diagnostic clues. Renal urinary disorders, obstructive disorders interfere with normal urine flow, so our ureters could be obstructed. Hydronephrosis is enlargement of the renal pelvis and calyces caused by blockage of urine flow. Renal calculi or kidney stones, crystallized mineral chunks. Make sure y'all read that. In order to see the bladder, we can put a scope down. This is what your bladder looks like. UTIs are often caused by gram-negative bacteria. Urethritis is inflammation of your urethra. Pyelonephritis, inflammation of your renal pelvis and connective tissue of the kidney. It may be acute or chronic. Chronic is autoimmune. Glomerular disorders result from damage to the glomerular capsule membrane of the renal corpuscle. Nephrotic syndrome accompanies many glomerular disorders. Proteinuria is protein in your urine. Hyperalbuminemia, low plasma protein level. Edema, tissue swelling caused by loss of water from plasma as a result of hypoalbuminemia. Acute glomerulonephritis caused by delayed immune response to streptococcal infection. How many times have we seen that? Chronic glomerulonephritis is a slow inflammatory condition caused by immune mechanisms and often leads to renal failure. Renal failure or kidney failure, renal failure occurs when the kidney fails to function. Acute, abrupt reduction in kidneys. So there are times when people have come in, we've given them too strong of an antibiotic and didn't test it, and we burn their kidneys. So what they would do is put them on temporary dialysis, allow their urine to be cleaned out, so their kidneys could rest, and then they could go back to normal. It would take some time, but then they could go back to peeing normally. Chronic renal failure is slow progressive loss of nephrons caused by a variety of underlying diseases. Polycystic kidney disease, numerous fluid-filled cysts destroy kidney tissues as they grow. This is usually hereditary. Kidney failure stage 1, early in this disorder. Healthy nephrons often compensate for the loss of damaged ones. So if you've got like 2 or 3, then you've got their neighbors trying to compensate, trying to help out and take over for them. Stage 2, often called renal insufficiency, is the loss of kidney function, ultimately results in high uremia and is has life-threatening consequences. Stage 3 is called uremia or uremic syndrome. Complete kidney failure results in death unless a new kidney is transplanted or an artificial is given. All right, we done, y'all.